The hardest thing to buy in AI is not a chip. Order a large power transformer today, and the site it powers switches on near the end of the decade. Before 2020, that wait was under a year. The industry now measures it in weeks, 128. The bottleneck is not the factory that assembles them, it is the metal inside, and how few places can make it. Start with what a data center needs before it can draw a single watt. Between the transmission line and the building sits a box the size of a small house, a large power transformer. It steps transmission voltage down to something a campus can actually use. Nobody photographs it. Nothing runs without it. By the industry survey from Wood Mackenzie, the average wait for one is now 128 weeks, 2.5 years from order to delivery. In the same survey, a generator step-up unit, the transformer that lifts power out of a station and onto the grid, runs 144 weeks. For the largest orders, buyers are quoted up to 4 years, and sometimes more. Before the pandemic, the same equipment arrived in under a year. The price moved with the queue. Wood Mackenzie puts large power transformers up 77% since 2019. Demand moved further. Substation transformers up 116%. Generator step-up units up 274%. That is the shape of a shortage. The thing gets slower and more expensive at the same time. For a hyperscaler, this reorders the whole project. Capital is available. Land is available. Permits are slow, but they move. The transformer is the item that cannot be hurried, and it sets the date the building opens. Utilities now order years ahead and hold factory slots before the final design exists. Which raises the obvious question: why can nobody simply build more of them? The answer is not in the factory, it is inside the box. Open it and two things matter: copper wound in coils, and steel stacked in a core. The copper carries the current. The steel carries the magnetic field between the coils. That field does not sit still. It reverses with the grid 50 or 60 times every second. Every reversal drags the magnetism of the steel around with it. Ordinary steel resists that. Its crystal grains point in every direction. Turning them costs energy, and that energy leaves as heat. Heat here is not a side effect. It is loss, power that entered the transformer and never came out as electricity. A transformer runs for decades. A small percentage, held for 40 years, is an enormous number. So the steel inside is not ordinary steel. It is grain-oriented electrical steel, and the name is the whole trick. The grains are aligned, rolled and annealed until they face one way. The field then travels along what physicists call the easy axis, magnetizing the steel with far less effort and far less waste. Turn the field 90 degrees to that axis and the advantage disappears. Which is why the core is not one lump of metal. It is built from sheets, cut and stacked so the field always runs the way the grains do. The sheets are thin for a second reason. A changing field induces little circular currents inside the steel itself, eddy currents. They do no useful work. They only heat the metal. Thin laminations, insulated from each other, cut the loops those currents can make. Thinner sheets, smaller loops, less loss. So the core is a stack of hundreds of coated sheets, each a fraction of a millimeter thick. Now the manufacturing problem becomes visible. This steel is not a grade you can substitute. The alignment comes from the mill itself, the rolling, the chemistry, the annealing, the coating. You cannot machine it in afterwards, and you cannot print it. A transformer factory can add a winding line in a year. A mill that makes this product is a different kind of asset entirely. In the United States, that mill is singular. One company makes grain-oriented electrical steel here, Cleveland Cliffs, at Butler Works in Pennsylvania. One plant for the entire country. Industry and Commerce Department estimates put domestic production at roughly a fifth of what the country needs. The other 4/5 arrive by ship. Worldwide, the producers of this steel at meaningful volume are counted on the fingers of one hand. The transformers follow the same pattern. By the same industry survey, about 80% of large power transformers used in the United States are imported. So the queue is not really a factory queue. It is a supply chain that narrows to a handful of mills. This is also where policy enters, and it is worth stating carefully. In August 2025, the Commerce Department added laminations and cores made of electrical steel to the derivative products covered by Section 232. 407 tariff codes in one action. Cleveland Cliffs had asked for it. Its argument was that neither Mexico nor Canada melts electrical steel, yet laminations and cores kept arriving from both. The effect is plain. The metal and the parts cut from it are now treated the same at the border. Then, in April 2026, the tariffs moved to full customs value. With one exception, for industrial and grid equipment, transformers, switchgear, the rate was set at 15%, temporarily, through the end of 2027. The stated reason: to support the build-out of production inside the country. Read the two decisions together and the shape appears. A tariff on the metal and a discount on the equipment made from it until the end of 2027. Both are coherent on their own. Both admit the same thing. There is not enough of it here yet. And by Cleveland Cliffs' own account, this steel is close to a quarter of the cost of a transformer. So the box that carries AI to the grid depends on a material one American plant makes. You can expand an assembly hall. You cannot conjure a mill. The money has arrived. That part is no longer the problem. In June 2026, Hitachi Energy broke ground on a $457 million transformer factory in South Boston, Virginia. It will be the largest facility of its kind in the country, and about 825 people will work there. It starts production in 2028. Read those two dates next to each other. Ground broken in 2026. Output in 2028. The cure for a multi-year queue takes multiple years to install. It is not an isolated bet. Hitachi Energy has committed more than $1 billion across its American operations and more than $1.5 billion to transformers globally through 2027. The order books say the same thing from the other side. GE Vernova booked $18.3 billion of orders in the first quarter of 2026, up 71% organically. Its backlog grew by $13 billion in a single quarter. A signed order is not a delivered transformer. Steel has to be melted, rolled, and coated. Cores have to be stacked by hand. Coils have to be wound, dried, and tested at voltages that find every mistake. And the people who do that work are not quickly replaced. The trade is aging, and training takes years, not weeks. Capital can be raised in a quarter. A furnace cannot. Which is why the queue has not shortened as fast as the spending grew. So where does that leave the machine everyone is building? Go back to the box between the line and the building. It is not exotic. Copper, steel, and oil, in an arrangement a century old. What makes it scarce is one layer, the steel, made in very few places, and in America in a single plant. The industry is fixing that. The fix is measured in years, and it started this summer. A chip is designed in 2 years. The box that switches it on takes 4 to arrive. Not blocked by silicon, waiting on steel and on the calendar that steel keeps. Next time, the substation it plugs into, and the queue to get connected at all.